Today we're going to start with the on-off control that we did last time in lab, and we're going to modify this code to do proportional control. Proportional control is what the P in PID control stands for, and it means that we're going to change the motor speed based upon the distance between where the slider is and where we want the slider to be. In order to do proportional control, the first thing we need to do is we need to create a variable that will tell us how far away the slider is from its target position. Now, we already have a target position implicit in our if-else statement that we used in on-off control, but today we're going to make it a little bit more explicit so that we can tell what our target position is and what our actual position is. So to start out with, I'm going to go up here to the sensor value, and I'm going to change sensor value. Instead of calling it sensor, I'm going to call it actual position. And I'm also going to create another variable that's also an int 16 that's called target position. Now, because our position down here can range between 1010 and 1035, this is setting a target position that is halfway between these 2 points. So I'm going to go up here to where I have target position, and I'm going to set it to the halfway point between 1010 and 1035. Now, the actual halfway point is 1022.5, but this has to be an integer, so we're just going to set our target position to 1022. Now, down here where we have the sensor value, we changed that sensor value to actually be called actual position. So I'm going to make that change here. Now, inside this loop, I have both actual position and target position. I'm going to calculate something called the error. That means the difference between the target position and the actual position. I don't want my error to ever be negative, so I'm going to start by checking to see if my target position is greater than the actual position or the other way around. If the actual position is greater than the target position, then error is going to be equal to the actual position minus the target position. This way, the error will be positive. Now, I haven't declared error yet, so I need to make sure I go back up here, and I'm going to create an int 16 called error. So back down here, I can say else, that is, if the actual position is less than or equal to the target position. In that case, I want to calculate the error the other way around, as target position minus the actual position. Now we can take these two lines that turn the motor on forwards or backwards, and I'm going to cut them, and I'm going to put them into either the if or the else. So this one that I just cut was from the case where the sensor value, that is our actual position, is less than the target position. So that one's going to go here where the actual position is less than the target position. Then I'm going to take this other one. This is what we do in the case where the actual position is greater than the target position, and I'm going to put that one here. Then we can go ahead and delete actually all three of these ifs and elses. So far, our controller is basically doing the same thing that it was doing before. If the actual position is greater than the target position, we're going to move the motor in one direction at a constant speed. Otherwise, we're going to move the motor in the other direction at a constant speed. Now, the thing that really makes proportional control different than on-off control is that we get to change the speed here based upon the error. We would like it to be that when the error is big, the motor will move fast to get closer to the target position fast. But when the error is small, we want the speed to be small. So we could actually delete this speed and just type in error and make the error be the speed. This will achieve our objective of having the motor move quickly when the error is big and have the motor move slowly when the error is small. Notice also that this will make the motor come to a complete stop in the case where the actual position is equal to the target position. When the actual position and the target position are the same, the error will be 0. And so we'll be writing the speed as 0 when the error is 0. That's why we don't need this third else to turn off the motor. Now, before we actually go and run this, there are a couple things we need to do. First of all, we need to do some thinking about what speeds we'll be sending to the motor. Remember that we don't ever want to set the speed higher than 100 because the speed here is a percentage of the motor's maximum speed. If we set the speed to be greater than 100, we're trying to tell the motor to move faster than 100% of its maximum speed, and that doesn't make any sense. Let's go back up to the top and let's create another variable. And let's call this variable speed. Instead of directly writing the error as the speed, let's do an intermediate step. Let's first set the speed equal to the error. Then let's check to see if the speed is greater than 100. If the speed is greater than 100, we'll set the speed equal to 100. That way, we'll never have a speed greater than 100 to send to the motor. So instead of directly writing the error as the motor speed, we'll write speed to the motor. We need to do the same thing down here. Okay, now lastly, we have to deal with these two errors here. These errors are happening because we still have sensor here, and we've changed sensor to be actual position. Now, go ahead and build your code to look for errors. After you've built the code and cleared up any errors you might have, click to program the PSOC and watch the motion of the slider. If you run MATLAB at the same time as you do this, you can also get the time response of this motion. See if you can calculate the overshoot, the settling time, the rise time, and the steady state error of the motion. Now, I'm going to show you one last change we can make that can adjust the properties of the motion. Here, we have speed being equal exactly to error. We could actually take error and multiply it by some value that's called a gain to make the motion be either faster or slower, and it will also affect the stability of the motion. We're going to multiply error times a value that we'll call Kp. And we're going to do that in both of these two, in the if and the else. Then, up at the top, we're going to create the variable Kp, and we're going to give it a value. Now, if we give Kp the value 1, the motion will be exactly the same as what you saw the last time you ran this code. If you make Kp bigger, say 2, the motion should be much faster, and it will also be less stable, but it will also be more accurate. In other words, as you increase Kp, you should see an increase in the speed, an increase in the overshoot, and you should also see a decrease in the steady state error. Likewise, you could make Kp be less than 1. Try making Kp be a value like 0.8 and run the code again and see what happens. As you reduce Kp, the speed should slow down. So, in other words, the rise time should become longer. But you'll also see a reduction in the overshoot, and you'll also see an increase in the steady state error. Try a couple of experiments where you try different values of Kp, run your code, and then calculate the values of overshoot, rise time, settling time, and steady state error, and see if you can get the trends that we expect as you change Kp.